Okay, hi guys, my name is Xiaoli. I will introduce the red and the black tree. So, what is needed of the red and black tree? We have already learned many types of trees, such as binary tree, binary search tree. First of all, trees is what? It is a data structure. You can say data structure means it's a way of organizing the data, or you can see a way of organizing the data efficiently in such a way that we can access the data in list time. We can insert something, we can delete something in a list time. Obviously, we want that if we are going to store data somewhere, then we want that we can search something from that data in a very least time. So if you are dealing with a large data, you need a data structure. We already learned like arrow, linked list. Every data structure is having its own advantages. Okay, so back to the topic. A red and black tree is a kind of self-balancing binary search tree where each node has an extra bit, and that bit is often interpreted as the color red or black. These colors are used to ensure that the tree remains balanced during insertion and deletion. Although the balance of the tree is not perfect, it is good enough to reduce the searching time and maintain it around big O log n time, where n is the total number of elements in the tree. This tree was invented in 1972 by Rodolph. The concept of a balancing tree was first invented by Helson-Wilsky and Lindes in 1962. They came up with the AVL tree. In 1970, this guy invented the 2 and 3 trees, another balancing search tree. The red-black tree was first invented by Rodolph 1972, who called them symmetric binary B trees. In 1978, this guy and Robert came up with the term red-black binary tree. So red and black tree is a special binary search tree. Each node of the red-black tree has a storage bit to indicate the color of the node, which can be red or black. Sorry. First, let me talk about the feather of red and black trees. This picture is a good red and black tree example. We can see that each node is either black or red. The node is black, each left node is black. If a node is red, its children node must be black. Every path from a given node to any of its descendant neo-leaf goes through the same number of black nodes. So second, application of red and black tree. Red and black trees are widely used mainly to store ordering data. It's very effective. It is very efficient. For example, the tree seed and tree map in Java, the seed and map in C++, and the management of Linux virtual memory are all implemented through red and black tree. Next is time complexity. The red and black tree time complexity is big O log n, and the search time is big O log n, insert time is big O log n, and the remove time is still big O log n. So we can simply think about that. For a balanced binary search tree, its time complexity is big O log n, and as a red-black tree, there is a worst case. During the search processing, the past nodes are all 3 nodes in the original 2 and 3 tree, which lead to the path to be extended twice, and the time complexity is big O 2 log n. Since the calculation of the time complexity can ignore the coefficient, the search time of the right black tree is still big O log n. Next, why we need a right and black tree. First, let me talk about the balanced binary tree. It has all the feathers of the binary search tree. The height difference between the left subtree and the right subtree of each node is at most equal to 1. For example, this is a binary tree. The first picture, it is a binary search tree. The time complexity is big O log n. However, in second picture, the binary search tree has been changed a chain structure. We can see that it looks like a chain structure. So now the time complexity is big O n. We don't want to do that because it is with time. So we use a balanced binary tree to make sure the time complexity is still big O log n, like the third picture. But the second rule of binary, but the second rule of balanced binary search tree is a strict requirement. So it will break the balanced binary search tree structure when we insert or delete node. That's why we need a right and black tree. Because right and black tree can use left hand rotate or right hand rotate to keep itself's structure balanced. Here are two examples to show how turn left node acts. The first, his right child node becomes father. Second, his grandson node becomes his brother node. We can see that the 40, how we turn left the 40. Turn right is very similar. The only difference is his left child node becomes his father node. We can see the Y, how we turn right Y, and how we turn right the 120. Like how to insert the data in the right and black tree. First, you have to insert the node similar to that in a binary tree and assign a right color to it. Now, if the node is a root node, then change its color to black. But if it does not, then check the color of the parent node. If its color is black, then do not change the color. But if it is right, then check the color of the node's ankle. If the node's ankle has a red color, then change the color of the node's parent and ankle to black, and that of grandfather to red color, and repeat the same process for him. We can see that the ankle is right, so we need to change the color of X parents P and ankle U to black. Second, we need to change the color of its grandfather G to red, and repeat the all recoloring steps for grandfather considering it as X. But if the nose ankle has black color, then there are 4 possible cases. The case 1, I call this left-left rotation case. In this case, the ankle is black, so we need the right rotation of grandfather G. Then swipe the color of the grandfather G and the parent P. In case 2 is a little different. I call this left-right rotation case. In this case, first we need left rotation of parent P. Then apply left-left rotation case. The left-left rotation case is case 1. So in case 3, it is right-right rotation case. In this case, we need left rotation of grandfather G, then swipe the colors of grandfather G and parent P. You can see in this picture, I think it is clear to show how we do that. In case 4, it is a right-left rotation case. In this case, we need to right rotation parent P and apply right-right rotation case. The right-right rotation case is case 3. Okay, the last but not least is delete. It is also have 4 possible cases. In case 1, if we want to delete the node A, we need to left rotate his father node. In this case, the A's father node is B, so we left rotate node B. In case 2, it's more easy. We just need to change his brother's color, black to red. So in this case, the node A's brother is D, so we change this his color black to red. In case 3, we right rotate his brother node. It is node D, so we right rotate the node D. In case 4, we just need to left rotate his father node and make sure the color is the same as the red-black tree structure. Okay, so it is my presentation. Thank you for your guys listening.